First problem asks us to calculate the work required to move a charge little q from far, far away to within a distance r of big Q. Now it's going to turn out that the forces, electrostatic forces, are conservative, so that the path doesn't matter. We don't know that yet. We haven't established it, but we will before the end of class, at least for a point charge. Well, we choose to locate our charge at the origin of the x-axis, and we're going to bring the charge in from far, far away to position x equals r. Now we put the charge arbitrarily at a point x equals x star. Okay, now how do we calculate the work required to move the charge from there to there? First of all, we got the suggestion from one of the class that the work is the average force times delta S, or more properly, the dot product of the average force dot delta S. Of course, we don't know the average force over this whole huge interval, but that would be, if we did, we'd be able to multiply that average force by the displacement, and or take the dot product of the average force with the displacement and find the contribution to the work corresponding to that displacement. Well, what do we know about force? Okay, we know that our delta S is going to be some motion along the x-axis from out there to in here. What about our force? Well, our force is just K, Q, little q, big Q. Now, suggestions from the class had r squared here. I used x squared simply because x equals r. R is going to be the fixed distance, or the distance to which the charge little q is moved relative to the charge big Q. Since we're modeling this by motion along the x-axis, x is going to be the proximity. Okay, because big Q is at x equals 0, so wherever little q is, that's going to be at some position x, and x is going to be the distance between here and here. Okay, so the magnitude of the force is K times big Q little q over x squared. We can depict the force versus position along the x-axis as an inverse square graph. R here is the distance that the proximity that we're going to end up with between the charge little q and the charge big Q. And we draw this graph and we imagine what it feels like maybe to move this charge in here. Okay, if I'm moving this charge little q, let's assume both of these to be positive charges, then I'm going to have an easy time if I'm far away, because there's not much force. Force falls off as the square of the distance, so it's going to be easy for a while, but then all of a sudden it's going to start getting hard, and then I know it's going to get harder very fast because of the inverse square relationship. So the force when x is large is small. As we move in closer and closer to the origin where the big charge big Q is, the force gets greater and greater. Now, if the forces are oppositely charged, I've got to hold this force back. Okay, so right now it's easy to hold it, but I get closer and closer, I'm going to have to exert more and more force, and pretty soon it's going to be really hard for me to hold that thing, and I'd better pull it back. If I get any closer, it's just going to pull me on in. Okay. That's the intuitive idea. Now, let's go ahead and calculate the force. We don't know how to find the average force over the whole displacement, so we're going to find the work done over a small increment delta x, where delta x is small enough that the force doesn't vary a whole lot from the force the force at one point of this delta x interval doesn't vary much from the force at any other point, so that we can make a very good approximation to the work done for this interval by letting x equal x star, where x star is any x coordinate within this interval. So x star is a sample point, x is going to equal x star, meaning that the force is going to equal k times little q times big Q over x star squared. So there's our force. Now I've got F dot delta x vector dot vector. Let me say that F would be k times little q times big Q over x squared times I, and delta x would be delta x times I. So it would be the dot product of this multiple of I and this multiple of I. Of course, I dot I is 1, so we end up with k little q big Q over x squared times delta x. So I didn't just ignore the fact that we have a dot product there. I wrote out the result. And you would want to write this out carefully with your I and j vectors and so forth. Okay, so we have F dot delta x is this. And that's over this delta x interval. Now, if we sum the F dot delta x over a bunch of intervals, we'll get a sum of expressions that look like this to get our total work. Now, that sum, in a way that you should be getting quite familiar with, is going to be the integral of k little q big Q over x squared dx between the limits. What are the limits? Well, one limit is, well, we're bringing it in from far, far away. So far, far away to distance r. We're integrating from far, far away to r. Now, what's another expression for far, far away? Well, I'm going to say far, far away is effectively infinity. So we're integrating from infinity to r of k times little q big Q over x squared dx. And the result is very straightforward. K times little q times big Q is a constant. Bring it out. We're integrating dx over x squared. We get negative kq times big Q over r times delta w. The details you can work out for yourself. The integral 1 over x squared is negative 1 over x. Evaluated at infinity, that's 0. Evaluated at little r, then it's this. And that's going to be your work. It's important to understand that this is the work done by the field. Okay, so this F is the force exerted by the field on this charge. The work done by the field, the work I do is I move the charge closer and closer and closer, and that's going to push me back. Okay, the work I do is equal and opposite to the work done by the field, because I'm pushing this way and moving this way. I'm doing positive work if these charges are both positive. Now, if they're negative, then I'm doing negative work because I'm holding it back, pulling this way while the charge is moving that way. Either way, the field is exerting a force in this direction as the charge is being moved in this direction. So the field is doing negative work, again, assuming these charges are both positive. Now, if they're unlike charges, and I think I said that right before, but if one of these charges is negative and the other is positive, then the field is pulling this way, and we're moving this way. So the field is doing positive work, but of course, since I'm holding back, I'm doing the negative work. Okay, so we want to be clear on the sign of the work and exactly what work this is. This is the work by the field, and I make that note here, work by the field.